Thank you very much, Maya, Robert, for the kind invitation to this webinar. So today I'm going to briefly introduce one of the technologies we have been working for several years. It's related to biogas purification, but also related to the topic that Gabriel presented, microalgae-based wastewater treatment. Okay. So just a brief overview of biogas production in the world. Okay, it's a growing topic. I'm going to use the light. It's a growing topic. The world production of biogas accounted for 17 million tons of oil equivalent in 2011, and it reached almost 33 million tons of oil equivalent by the end of 2002, with where Europe was the leading region in the world producing biogas, but Asia Pacific exhibiting the largest growth in biogas production. This slide, you can see the rapid growth of biogas plant, which number rose from 6,500 plants in Europe in 2009 up to almost 17,000 by the end of 2014, mainly in Germany and Central Europe, and then a slow increase in the number up to almost 19,000 plants in Europe by the end of 2021. Okay. If we analyze the volume, the flow rate of biomethane produced in Europe, we can see that the production exponentially increased from 0.5 billion cubic meter of biomethane in 2011 up to 3.5 billion cubic meter by the end of 2021. Okay, we look at the world. Then the production increased from 0.5 billion cubic meter up to 7.4 billion cubic meter by the end of 2021. Okay. So regarding the technologies to purify the biogas and convert it into biomethane, by the end of 2021, CO2 separation by membrane was the leading technology, followed by pressurized water scrubbing, chemical scrubbing, and pressure swing adsorption. Okay. When analyzing the CapEx, the specific investment cost of biogas upgrading technologies, we can observe a very clear and severe economy of scale effect. Okay. Only when dealing with a large flow rate of biogas above 1,000, 1,500 normal cubic meter per hour, the specific CapEx decreased below 1,500 euros per normal cubic meter per hour of treatment capacity. Okay, for plants in the medium to low range, the CapEx, the specific CapEx is very, very high. Okay, in terms of electricity consumption, most physical-chemical technologies exhibit a range of 0.2 to 0.3 kilowatts-hour of electricity per normal cubic meter of biomethane produced. Okay, so this is for this. I mean, this figure is similar for pressurized water scrubbing, for pressure swing adsorption, for membrane separation, for organic solvent separation. The lowest electricity cost is for chemical scrubbing. However, in order to regenerate the solvent, we need a significant heat input. Okay, around 0.5 kilowatts-hour of heat energy per normal cubic meter of biomethane. Overall, we have to spend between 3 and 12% of the energy content of biogas in order to produce biomethane with a quality suitable to inject in the natural gas grid or to use as a vehicle fuel. Okay, so in this techno-economic context, we need to develop innovative, low-cost, and environmental-friendly technologies, more sustainable, in order to convert biogas into biomethane in small and medium-scale plants, which represent most of the plants in Europe. Okay, so the technology we have been working in Valladolid for the last 10 years consists of introducing the biogas, mainly composed of methane, around 60-65%, CO2, 25, 35, 40%, and hydrogen sulfide, which is toxic and corrosive, into the photobioreactor at a high pH with a high buffer capacity. Carbon dioxide and H2S are acidic acid that rapidly dissolve into the cultivation broth. In the presence of light, microalgae fix carbon dioxide, produce oxygen, which is used by sulfur oxidizing bacteria to oxidize hydrogen sulfide into soluble sulfate. Okay, the nutrients needed to generate algal biomass and bacterial biomass can be provided by the liquid fraction of the diastase. Okay, so in this way we can produce an algal biomass that can be used as a bioenergy feedstock or a biofertilizer, biostimulant feedstock. Okay, the technology is implemented in a two-stage system where the biogas is introduced into an absorption column, which is mainly a bubble column, using recirculating the culture brought from the high-red algal pond. So in this way, the carbon dioxide and hydrogen sulfide dissolve from the biogas to the liquid into the liquid. Hydrogen sulfide is in situ oxidized by bacteria using the dissolved oxygen in the cultivation broth, while carbon dioxide just dissolves, okay, and is conducted to the open pond where CO2 is fixed by microalgae in the presence of light. Okay, a key operational parameter to control the quality of biomethane is the biogas to liquid ratio. Okay, we did a preliminary analysis, okay, assessing the influence of the liquid pump into the column versus the biogas introduced into the column. Okay, and we can observe that at high pH and at a high buffer capacity, carbon dioxide removal is almost complete regardless the liquid to biogas ratio in the tested ratio from 1 to 60. Okay, interestingly, the methane concentration decrease, okay, when increasing the liquid to biogas ratio until reaching the biogas content, which was about 30%. Okay, this decrease in methane content at 100% removal efficiency of CO2 was due to the stripping of oxygen and nitrogen from the algal broth to the biogas. Okay, so in order to purify biogas into a high quality biomethane, we should work in this range of low liquid to biogas ratio. So by working in this range between 0.5 and 1, the methane content can be increased up to 98%, okay, while decreasing the nitrogen and oxygen strip out, okay, reaching a high biogas biomethane quality. Okay, in terms of hydrogen sulfide removal efficiency, the high pH value of the photobioreactor entails a very high H2S mass transfer and very high removal efficiencies of H2S. So we can reduce CO2 content and H2S content in a single stage process. Okay, the key environmental parameters in this system are the inorganic carbon concentration working at high salinity. The methane content produced in the column reaches above 95% methane content with CO2 content below 2%, which is the European biomethane standard. However, when working at low inorganic carbon concentration from 500 to 100 milligrams per liter of inorganic carbon, then the methane content remains below 75 and 80%, and CO2 content above 17, 22%. Okay, so this technology has been gradually scaled up from our lab in 180 liters to a pilot reactor in the facilities of 𝐌𝐤𝐜𝐜 within the European project in 𝐶𝐫𝐫 in the wastewater treatment sector. Then we also tested this technology in the urban waste treatment sector in a 270 square cubic meter. And we are currently validating the technology in the livestock sector in a 1,500 square meter photobioreactor within the live project Smart Agro Mobility. Okay, this is a picture of the demo plant where you can see here the algal photobioreactor, the biogas absorption column, and the biomass settler. The removal efficiencies when testing this technology with domestic wastewater, okay, it's ranges between 50 and 90%. However, when working with centrate, the removal efficiencies at pilot scale remain significantly higher, around 95, 100%. Okay. Within the European project in 𝐶𝐫𝐫, we also develop a control strategy to be able to provide a consistent biomethane quality versus variation in the biogas flow rate. Okay, so by simulating a gradual increase in the biogas input into the column, like this one, from 150 to 400, and analyzing the biomethane composition and controlling the liquid pump injecting liquid from the photobioreactor to the absorption column, we could control the biomethane quality. Okay, so this is, the time course of CO2 concentration when an increase in biogas flow rate occurs. You see it increases from 2.5% to 16% in CO2 with a concomitant decrease in biomethane content from 97% to 83%. However, when switching on the control strategy, controlling the liquid flow rate, the CO2 content in the biomethane remains below 2%, and methane content remains above 96%, okay, validating the control strategy. If we want to use the nutrients in the digestate, you know that digestates contain very high nutrient content, from 600 up to 4,000 milligrams per liter of nitrogen, and from 100 to up to 500 milligrams of phosphorus. Stoichiometrically, this digestate could render a culture density between 5 and 50 grams per liter. Okay, for those of you working with microalgae, this is a very dark culture with poor light penetration, low photosynthetic efficiency, which requires a fine-tuning of the process. Okay, what we did, okay, it's just in the same process configuration, introducing the biogas in the absorption column, but interconnecting the photobioreactor to the absorption column using a biomass harvesting unit in order to control the biomass concentration. Okay, so by controlling the biomass productivity using this biomass separation unit, okay, the increase in biomass productivity, this is an experiment carried out in the lab with low biomass productivity, but you can see that if we increase the biomass productivity from 2.5 to 7.5 grams per square meter per day, the removal of nitrogen from real centrate does not improve. It just remains above 95%, and the same for phosphorus. However, if we analyze the amount of nutrients recovered in the biomass, we can observe that we are fostering nitrogen fixation and preventing ammonia stripping or phosphorus precipitation. Okay, we did a preliminary sustainability analysis using a reference flow rate of biogas treated of 300 normal cubic meter per hour, comparing the technology, okay, high red algal pond interconnected to a biogas absorption column, compared to a conventional activated carbon filter for biogas desulfurization and a water scrubber for CO2 capture. We did some preliminary analysis using the 𝐼𝐜𝐴𝐚 metrics, estimating CAPEX, OPEX, and all emissions. And what we observe, okay, the land requirements of algal bacterial processes are significantly higher than conventional activated carbon water scrubbing. However, in terms of energy consumption, the energy cost of biogas purification decreases from 0.3 cubic meter per hour, kilowatt hour per normal cubic meter, down to 0.08 kilowatts per hour per normal cubic meter. Okay, if we translate this into money, the operating cost decreases from 0.2 to less than 3 cents of euro per normal cubic meter of biogas treated. Okay, and as a take-home message of this presentation, the purification of biogas is dominated by physicochemical technologies which exhibit high operating cost and high environmental impact. Algal bacterial processes have now a similar CO2 and H2S removal and high robustness, but with lower operating cost, lower environmental impacts. The need for biogas conditioning is much less severe in algal bacterial systems. Technology tested at pilot and semi-industrial scale with an associated recovery of nutrients. Okay, we can remove H2S and CO2 simultaneously. Alkalinity, pH, and liquid to biogas ratio were identified as key operational parameters, and we can improve the robustness of the technology using the right control strategy. So thank you very much for your attention.